Okay, so you go to that down arrow now, Fahad. Click on English.
Yes, sir.
Hmm. Yeah, go to devices. Devices.
Want to share?
Yeah, go to F2. Yeah, yes. F28379D. Yeah, so say now.
Yeah. I was saying whatever Fahad was asking, you can clarify that doubt in this session, okay?
Yeah, yeah,
Because
sure.
everyone will get it.
Yeah, yeah, sure, sure. I'll say that. Yeah. You just turn off your mic. Okay, examples. Go to examples. And then bit filled and CPU one. Okay, now you import any of one of the example. Yeah,
Which
just
one, sir?
import if Blinky, anything you can import. Import Blinky as yeah, import it. Okay. Now you go to that particular uh, project. Yeah, down arrow. Click on main file. Yeah, double click on it. Yeah, no, what you do is you press that build button. Press the build button. Yeah, yeah. And now you can press that debug button. Okay, it is building. Let it get built. Yeah, it's fine. Now you can debug with that button. Yeah, just click on that. Yeah, okay. Yeah, I think it's fine, Parth. It's working fine. Okay. Yeah, you can click on green button now.
Which one, sir?
The green button, which is the resume button. Can you see just below the view tab? There is one green button just below the view tab.
This one.
Yeah, yeah, that one. Yeah, that one. Yeah, yeah. Now your code is running.
Yes, sir. The blue LED is blinking.
Yeah, yeah, yeah. So you don't have to do anything extra. Okay, already there is one connection file and everything is there. So you don't have to do anything extra in here. Okay.
Sir, connection file. I am not getting.
Connection file in the sense that target configuration file is there now.
Okay,
You
okay.
click
This
on
one.
that.
Okay.
Yeah, yeah. So it's already there. Okay. So the board is already selected. Maybe somebody has used this board previously. So it's
Yes.
already there, active by default. Okay.
Okay.
So you don't have to change anything in there. Okay. Yeah. So you can stop presenting for.
Okay, sir. Okay,
I'll
sir.
start today's session. GPIO pins
Yes.
present onto this microcontroller, and then we saw GPIO and peripheral muxing, like what GPIOs we can use onto the board and how can we assign it to particular peripheral that we saw. Like from here we saw when mux value is set to 0, it is particularly a GPIO pin, and if it is set to 1, it will be a EPWM pin. So the mux is divided into two categories as we saw yesterday, that is normal mux and Gmux. And then we looked at the interrupt, that how core interrupt is processing with the help of IFR, IER, and INT in global switch. So we looked at this logic. After that, we saw how to program particular register in order to enable and disable it, and we saw how to trigger an interrupt with the help of peripheral interrupt expansion module, which is basically with the help of pi assignment table or pi vector table. So from this pi vector table, with the help of group and subgroups, we used to trigger a particular interrupt, and then we used to perform any operation if we want to perform. We saw an example of CPU timer yesterday, where we used to configure CPU timer at a particular interval of time in order to trigger an interrupt. And then we wrote a certain set of code over there, that is to toggle a particular GPIO, which was assigned as a blue or red LED. And that's how we executed a code. So we saw a basic background of this, and looking into the software looking into the software. So we saw that file is how to create a new project from this particular file, how to import any existing files if it is there in your workspace, then how to add new header files into a project. Like if you right click any of the project, and if you go on, it's a little bit handy, so it's working a little slow as my Matlab is also open. So we saw how to create any particular new project with respect to this particular software. Then we saw how to debug your code, and as well as we saw how to import your example from Resource Explorer as well. Then we saw how to use these expressions, variables, and resistors. So we basically put our all things into this variables column, in which we used to see what is the output of your algorithm. And we as well saw about C2000 there, how to import your project from C2000 there. Okay, now in today's session, I'll explain a little bit about Matlab as well. Like if you want to install this particular package into Matlab, what you have to do. So for installing a package into Matlab, you have to go to Add Once from your Matlab window, and then you have to click on Get Hardware Support Packages. So if you click this tab, another window will open, which will ask you which package to add. It will take some time. So whether you are using 19, 20 or 21 MATLAB, okay, all the CCS version below 9 will actually are supported over here. 11, I guess it might support. You can try once. So in the search add-ons button, you can just search for C2000. And after that, this is embedded coder support package for Texas Instruments C2000 processor. You can download it from here. If you click this, okay, it will ask here install. I have already installed it, so it is asking me manage. So after installing it, something like manage will come. If you click on manage, you just have to select the board which you are using and all, and it will get connected to your this particular MATLAB. So you will as well get one YouTube video as well if you see how to connect your microcontroller to this particular C2000 processor. So this is the basic procedure. It will not take as hard. Okay, so you just have to manage, and then you have to, if that software is installed, it will show something like this. Yeah, it will show something like this. So you can go to setup. After clicking on setup, since I have already done each and every setup, I don't know what next it will show, but I guess it will show only settings, whatever you want to do. So in any system, MATLAB works a little bit slow. If your processor is higher, then it may work a little bit fast as well. Since I'm using i3, it's little slower. So yeah, select processor family. This will a new tab will come like this. So from here you have to click on only TI Delfino F28379D. All the other boxes you have to uncheck, and then you can click on next, and then you can set up. I have already set up, so I don't want to repeat the procedure over here, as it may cause any mal-operation while I'm explaining the code. Since these are very sensitive connections, once you have done, you don't have to touch anything of this. Okay, so once you click on next, you will get certain things over there, in which you have to specify the location of your CCS that you can browse and specify, and then it will finish. So it's a very easy procedure if you have to install your CC Studio into this one particularly. And if you want to see how a code is running onto this particular thing, you can go to Simulink, and I'll explain certain settings that you need to do before dumping any code. So MATLAB is very easy, and you will get lots of resources, as MATLAB is a widely used software. So you will get everywhere whatever you want to have any interface with that. We'll see about EPWM module today in brief. Mostly I'll try to cover it in a less period of time, and I would also like to watch you one video after that so that it will be totally clear to you what exactly EPWM is. So it is taking some time. We'll wait till then. So before, so till that time, what I would like to tell you is this is also running slow because of Matlab. So I have to first close Matlab before explaining anything. So let's just deal with the Matlab first. You try to install C2000ware package into your Matlab. You try to integrate your board once your hardware board arrives. If your vendor supplies it early, it will be very nice. Even if he doesn't give you right now, there is no issue. What we'll do is this group will be active even if the workshop gets over, so that even if you have any doubts, you can ask me anytime. And if that doubt is within my reach, I'll try to help you. So it is not necessary that you have to watch the videos and then only ask me. Okay. After some time, also after some duration, also you can ask me. So whenever you get time, you kindly go through all the videos and learn how to make your own code into this, as you are all aware of how to trigger an interrupt now. Is there any doubt with all the interrupts that I've explained till now to anybody? Shankar, do you have any doubts? I guess he's not here.
No doubts from
Sir,
my
I'm
side,
going
sir.
through the video, uh,
Okay,
so I'm not in a position to say that I have a dog. So,
okay. Have you not watched all the videos, Fad?
sir, I had attended the session, but yesterday I was doing some work in parallel as well,
Okay,
so
okay,
I
okay,
have to
okay.
watch again.
Okay, fine. No issue, no issue. I hope videos are understandable to you
Yes,
guys.
sir. Yes, sir. Yes, sir.
They are understandable, right? Okay, fine. So, Muthuga Swami, do you have any doubt till this session? Is there anything that you would like to ask? Okay, I think he's also not here. Siddharth, do you have any doubt?
No, sir. No doubt from my side also.
Okay. So if you face any issue regarding downloading or anything, you can ask, okay?
Okay, sir.
Yeah. One more thing I would like to tell you guys is once you watch all the videos and once you clear with the interrupt and everything, it will be very easy for you that if you want to generate any logic for any code, like you can think on your own how to generate any particular. Okay, Mr. Swami, I got your message. So I'm saying if you really want to think about this, that you want to generate any particular code onto the something, so you can as well do that. So is my Matlab screen visible to you guys?
Yes.
Okay.
Yes, sir.
So I will just import one of the model that I have created yesterday. So if you go to model settings, you have to wait till that model gets imported. Okay, it's the same file. Okay. Just hold on a second. Whenever is Matlab adjoined with any other CCS software, it will work very slow. We can work on only one system. Okay. I did not know much about Matlab, frankly speaking. So I have just watched some of the videos in order to explain to you guys. As I have been always working in CCS only. So whatever my algorithms and everything I just make it in CCS only. Like you can see from here as well. If I have to make code like SPPWM for my inverter, I will just do it here. If I have to make any code for ADCs, anything, I will just do it here. Even if motor codes are there for any BLDC or any motor, I will just take the examples and I'll try to do my code on my own. So RSPWM is also there. It's a remote state PWM technique for inverter. So we'll see how actually this PWM SVQ can implement. SVPWM CMP elimination is also there for dual two level inverter. Is somebody who wants to say something?
Sir, earlier you had once mentioned in the workshop that
Hmm.
if we use through Matlab,
Hmm.
it has to access the CCS package anyway. So,
Yeah.
what is the reason usually for doing this through Matlab?
No, actually, some of the people wanted to know how to integrate the board to Matlab as well, because
Okay,
Matlab is a kind of GUI environment. Now it provides you more easy way in order to implement your algorithm, because you just have blocks
yes.
and you can connect them. So it's a very easy way to implement your algorithm. So that's why we are teaching this, as it was not a part of course as well, and I not much aware about this as well. But as per Som's request and other participants' request, I looked into it. So basically, if you go to this is one of the code that I saw, and it includes two GPIOs. These GPIOs I have taken from library browser. So if you go to library browser, in that particular library browser, you will have a embedded coder support package. From this embedded coder support package, if you go to F28379D, which is our board, you can see here the GPIO is listed as digital output. So you can click on that and you can add it to your model. So once you add it to your model, and if you double click this, it will open its own setting that which GPIO you want to trigger. And as per our presentation that we saw that our blue and red LEDs are particularly GPIO number 31 and 34. Blue is 31 and red is 34. So from this, we are triggering both the LEDs. So in this model, I have taken GPIO 31 and I have clicked on toggle option as well. And I have clicked on apply and OK. Next GPIO digital output, I have taken GPIO 34, which is a red LED. So this is blue LED, this is red LED. So this code will blink these two LEDs. I'm giving one constant input from here, setting sampling time as 0.5. And in signal attributes, you have to just click on output data type as unsigned integer 16-bit data, that is 0 to 2 to the power 16 values it can take. Then you can go to your hardware settings, and in hardware settings you need to make some changes over here. Like if you are going to hardware implementation, you need to select your board. So it's working a little slow, please have patience with me. Yeah, so from here you can see I have already selected TI Delfino F28379D board. You have to select device vendor as Texas Instrument and device type as C2000. And after that, in this math and data type, if your code is not running or showing any error onto the flush to zero option, you click on gradual underflow. It's your simulation behavior basically. So if any error is showing in your code, you can go to gradual underflow instead of this flush to zero. I don't have much idea what exactly this means. So from this one, you can just click OK, and then there's one option over here that is build, deploy, and start. So you can build your code, and your LED will start glowing. So the basic example was to show that your both the LEDs will glow with this particular example if you try to do it. You try to do it on your own in Matlab once your board arrives and try to deploy the code. After dumping this code, you'll see that both the red and blue LEDs will start blinking. Okay. So since this is not expression of interest as of now, I'm not dumping it as it will take more time. So I'll just close it. I hope this was clear to everyone. Uh,
Yes.
yeah, okay. So so today we'll look into the EPWM module. So before learning the EPWM module, we need to have a basic understanding of what is counter and what is timer and how does they perform. Okay. So just to have a basic introduction to counters, I have shown here some slides to you that any counter is a combination of flip-flop basically. You must have studied flip-flop like SR flip-flop is there and JK flip-flop is there. So what does this flip-flops does is they store any particular bit like ones or zeros. They can use to store this particular bit. So the combination of these flip-flops are called as counters. So counters are the circuits basically that transfer any particular bit or byte through particular number of states, that how many depends on how many flip-flops you're connecting. So basically there are two types of counters. One is asynchronous, that is parallel counters, and one other one is synchronous parallel counters, asynchronous ripple counters. Okay, so you don't need to understand many things into this. What you need to just understand is a counter is something which is counting from certain value to the bit to which that counter is designed for. Let's say if it is a 8-bit counter, it can count from 0 to 2 to the power 8. If it is a 3-bit counter, it can count from 0 to 2 cube, that is 8. So counter can be counting from these particular values to any particular bit number which is for which it is set. Okay, then you can see the difference between asynchronous and synchronous operation. Asynchronous operation, every clock is fed to individual flip-flops, okay, separately. And in asynchronous counter, kindly hold for a minute. My laptop battery is getting low. I'll just put a charger. Yeah, so we're talking about counters. So saying about the basic operation of counters, you can see a clock pulse, okay, here. So you can see whenever a clock pulse is detected on its rising edge, so these are the rising edge of any clock and these are the falling edge of any clock. So whenever any rising edge is detected to any particular clock, your counter will start counting from 0 to that particular bit to which it is assigned to. If it is a 3-bit counter made up of certain flip-flops, okay, it will start counting from 0 to 2 cube, that is 8. And the time period of each clock will be denoted by T clock. So the basic need for understanding this counters operation is that there are certain timers and counters into this particular board peripherals which are used in order to generate any particular waves, such as let's say such as if you want to generate any particular triangle waves, asymmetrical triangle waves, and if you assume that this TB clock is very small, if it is very small, I have shown here little bit big in order to make you understand, but this timestamp is not very big, it's very less. So because of this, you can assume this as a particular slant like of wave, a symmetrical wave. So it will be rising from 0 to 8 in a slant way. Now, if you see, this is a one type of counter which is counting from 0 to 8, and then it is gone to reset mode, and then again it will start counting from 0 to any particular 8. So it goes stepwise, but since your clock frequency is very high, your TB clock basically will be very less. And this TB clock, which is actually the time period, if it is very less, you will see that only a single slant wave will be over here, not this step kind of waveform. Okay. Then there are two basic types of counters. One is count up and count down mode. In count up mode, your counter will start incrementing from 0 to 7 if it is a 3-bit counter. And your count down mode, your counter will start decrementing from 7 to 0. You don't need to understand many of the things in here. It's a very simple logic. Okay. We have to put our brains into designing algorithms whenever we are designing it. There are certain registers which are there for us and it is assigned for some operation. So how can we use those resistors for our purpose? That is our main aim. Okay. So the basic operation of counters, if you see from here, that if I say it is up down counter, it will count from 0 to 8 and then again it will count from 8 to 0. So this is up down counter example, and in this counter you can see you can generate a triangular wave easily. Like if TB clock is very less, your triangular wave will start from 0 up to certain value, let's say 8, and from the 8 to 0 again. So you can see a clear triangular waveform, symmetrical waveform you can generate with respect to this particular counters. So this is the use of any counter. Okay. So there will be certain videos available if you want to understand how exactly they work and what is their operation. But for this, you just need to understand a counter is something which is counting from 0 to certain bit to which it is assigned for. Okay. Then, yeah. So this was about the counters. Now, yeah, so this is our main module which we are going to learn about today, which is a EPWM module. So after explaining a little bit about this module, I would also like to watch you one of the video on TI's website. Okay, so first I'll explain here what exactly this is, and then we'll see how exactly the pulses are generating with this module. Okay, so first of all, EPWM module is a highly programmable module. It is referred to as EPWM, and its full form is Enhanced Pulse Width Modulator module. Okay. Now EPWM X here shows X particularly shows the EPWM module number, like EPWM 1, 2, 3, 4, 5, 6. If many modules are there, it will show from 0, 1, 2, 1, 2, 3 to 12. If 12 modules are there, then it will be EPWM 12, like that. Okay. Then you have other two inputs from here, that is EPWM sync in and EPWM sync out. Now this sync in and sync out is provided in order to synchronize your multiple EPWM modules together. Let's say you will be having two EPWM modules, but you want both the pulses of EPWM modules to start at the same time. Then you have certain buttons here like sync in and sync out that you can connect one to the previously, and you can connect its output to the other one. Like you can see here x minus 1, x plus 1. It means if you are at EPWM 2, this will be EPWM 1 and the lower version will be EPWM 3. So EPWM 1, 2, 3 will be connected together with this sync in and sync out option. So sync in and sync out is basically to synchronize all the EPWM modules together. Okay, so this EPWM module has itself this synchronization logic, and when this EPWM module has certain submodules into it like counters and timers that we'll talk about in few minutes, that will also have its own synchronization logic. So we'll see how to synchronize those PWM, as it is a main challenging task whenever you're going to implement any PWM. However, it's a very less instructions are required for that. But in order to understand that particular thing, it is important that you understand basics of counters and timers. Okay. So from here, I want to say that every EPWM module has two outputs, EPWM XA, EPWM XB. And this EPWM XA and XB, where X denotes the number of EPWM module, it is selected through GPIO mux. How it is selected through GPIO mux? We saw before that if in our GPIO resistor, if I am selecting any GPIO pin and putting 0 in front of it, it means that pin is assigned as general purpose input output pin. But if let's say I put 1 in front of that particular register, what will happen is that pin will be now assigned as EPWM pin. And which number of EPWM pin? That we saw. So from here, if you see that EPWM 4A is J8 pin number 80, which can be assigned as GPIO 6 if you assign 0 to any GPIO initialization, and if you assign 1, then it will be selected as EPWM 4. So you can see here all the PWM pins are in pair, that is 4A, 4B, 5A, 5B, 6A, 6B. Then you have here 1A, 1B, 2A, 2B, 3A, 3B. So EPWM 1, 2, 3 modules, they'll be connected together. Then you have EPWM 4, 5, 6. So these modules will be connected together. A basic logic for this connection, I would like to show you from technical reference manual itself. So what I want to show you here is this particular figure. Is it visible to everybody?
Yes.
Okay, so from here you can see your EPWM 1, 2, 3 modules. Okay, these are connected together. Now if you go for another thing, it will be like EPWM 4, 5, 6, these modules are connected together. So what it means is 1, 2, 3 are synchronized together. Okay, now if you want to synchronize EPWM 3 to EPWM 4, there will be different procedure. Okay, now if you want to synchronize EPWM 6 to EPWM 7, that will be different procedure. So these modules are connected together like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there will be total 12 EPWMs available to you. But now you will say that I just have here 6 EPWMs. How are you saying that there are 12 EPWMs? So as previously we saw, like if you go to GPIO and peripheral muxing, so from this table, you can see that 6A and 6B are available to GPIO 11. Yeah, it's fine. But if you go to 7A and 7B, EPWM 7A and 7B, from here you can see the EPWM 7A and 7B are titled as GPIO 12 and 13. So it means if your GPIO 12 and 13 pins are available to you, which I guess will be available to you. You can see from here, if GPIO 12 and 13 is available to you, you can use EPWM, particularly 7A and 7B as well. So from here we can see GPIO 14 and 15 is available to us. And okay, so from this GPIO peripheral function, you can see 14 and 15 is available to us. Yeah. So basically EPWM 8A and 8B we can use. So if you have 6 PWMs, it is not like you can be limited to 6 PWMs. You can as well use EPWM 8A and 8B. Then there are certain other EPWMs also limited to EPWM 12A and 12B that you can use from this table. From this table you can see if you are selecting your main mux like G mux as a 1 and you're selecting your normal mux as 0, 1, you can as well select EPWM 11B and EPWM 12A, 12B as GPIO 21, 22 and 23. So if you have your GPIO 22 and 23 with you, which you can see from here, like GPIO 19 is available to you, then from this one you can see, okay, that is not available to you. So certain pins are available to you, certain pins are not available to you. So whatever pins are available to you that you can use. Yeah, GPIO 19 and 18 is here. From this one you can see J1 pin number 3 and J1 pin number 4. So for 19 and 18, from 19 and 18 you can see you can use EPWM 10A and EPWM 10B. So there are certain EPWMs like 8A, 8B, 10A, 10B that you can use irrespective of this PWMs which are available to you, that is up to 6A and 6B. But for selection of this PWM, you have to click on your Gmux as 1 and you have to put your main mux as 1. So this will be setting configuration in order to initialize your 10A, 10B. We'll see how to initialize that through code as well. Okay, so I'll explain that in code as well. So basically this was about PWM modules available to you. Now the input to this PWM are through input crossbar, EPWM crossbar. Crossbar refers to something that is helpful for you in order to route your signals from one pin to another pin. Like let's say you have certain signal which is coming onto GPIO 14 and you want to transfer that signal to GPIO 15, you can use input crossbar. So into the board, if you want to transfer some signal, you can use input crossbar. Then you have EPWM crossbar, like from normal GPIOs to EPWM, this crossbar will be routed. So in order to transfer signal onto the board, your crossbar is useful. We'll see that as well through exercise, how it is there and how you can use that. So every module has its basic details. Okay, and it is not in a brief way. Okay, it is like you should understand it in an elaborate way in order to understand each and every module or submodule of this particular EPWM. So the output of this PWM, it can generate a start of conversion signal for ADC. ADC is an analog to digital converter and it is operated through a clock pulse only. So that clock is nothing but a start of conversion signal. So to generate that start of conversion signal, you can use EPWM. Now you're saying how, now I'm saying how you can use this. Let's say if you're generating certain pulse and it is having certain frequency of 10 megahertz and you want to have a sampling frequency of ADC as 10 megahertz, you can generate a EPWM SOC signal and you can use it as a sampling for your ADC, sampling frequency for your ADC. Then ADC will start sampling at 10 megahertz of frequency. So when your ADC is operating at a higher frequency, your time for your ISR to run, like interrupt service routine, that will be very less. Like 1 by 10 mega, that will be time for your ADC interrupt service routine to go and execute. I hope you understood this. What I mean to say by this is, let's say you have a 20 megahertz of frequency of ADC sampling frequency. So 1 by 20 mega, okay, that will be around 5 nanoseconds. So in that 5 nanosecond, ADC interrupt will be running. Like we saw in configure CPU timer instruction that I have explained to you previously, that in 50 milliseconds, you will be able to run any particular block of that CPU timer ISR. So that way, ADC ISR is triggered after the certain period of time, and that is your sampling frequency. And in that ADC ISR, that's why it is important that if your ADC has a higher sampling frequency, you can execute your code in less period of time. So where you have to deal with the nanoseconds, okay, you want your sampling frequency to be much higher. Then people go for CLAs and all other features. Okay. So you have CLA over here, that is peripheral interrupt expansion module CLA. So from this EPWM, you can as well generate an interrupt, which can be a trip zone interrupt, which is further given to PI module or CLA module. So what is a trip zone interrupt is, let's say you want to employ any overcurrent protection or over voltage protection into your board. So in that case, this trip zone is necessary. Like if you want to switch off your PWM at particular current or voltage, this trip zone can provide you that feature by two particular categories, that is one shot feature and cycle by cycle feature. One shot feature tells you that at one point of time when overshoot is occurring, at that point of time your PWM signal will be off. And cycle by cycle feature tells you that if you have prescribed some rating of the current and if that current particular rating is reached when your PWM is on, automatically your PWM off will be assigned. And once it has reached to certain lower limit, automatically it will again start turning on. Just like in buck converter, during turn on period and turn off period, if you see your inductor current, it will rise with certain slope and it will fall with certain slope. So that slope you can define and you can use this strip zone for that particular thing. So
Sir,
we'll see. Yeah,
sir, are you referring to the peak current
yeah,
converter?
yeah. I'm referring to the peak current part. Yeah. So okay, so this was about it. So I'll tell you how to use strip zone as well. Okay, and GPIO, we'll see how to initialize EPWM as through GPIO, and we'll see how to generate a start of conversion signal to ADC as well with the help of this EPWM. Okay, now from here you can see that I told you that this EPWM has two outputs, EPWM A and EPWM B. So these two particular outputs, how you can generate the pulses of this output, that we'll see. Okay. So this EPWM module itself, it has total 8 number of submodules. First is time-based submodule. Another one is counter compare. Third one is action qualifier, event trigger, deadband, PWM chopper, trip zone, and digital compare. Now you don't need to memorize everything in here. Okay. What you need to understand is what are the resistors that used to program this time-based submodule, counter compare submodule, and action qualifier submodule. Then this deadband, PWM chopper, trip zone, these are the other submodules that we'll see one by one. Okay, so first of all, we'll see what is a time-based submodule and what exactly it does. So from this time-based submodule, you can see that EPWM sync in option and sync out option is connected over here as well. So this time-based submodule will be present in each EPWM module. Like this is one EPWM module particularly. So like this, there are 12 EPWM modules that we saw now. And into this particular EPWM module, these are the submodules. Now there are certain functions or certain tasks that these submodules are assigned to do. Okay, like counter compare is there, action qualifier is there, this time-based counter is there. So into this time-based module particularly, this time-based module particularly has its own counter. Okay, so this time-based submodule has a 16-bit counter. What 16-bit counter means is it will be counting from 0 to 2 to the power 16 integer values. So it means you can store the value in that particular register from 0 to 2 to the power 16 any integer. Okay, now this time-based submodule has its own clock. Okay, see, everything works on clock. If you actually generalize, your microcontroller is also working on a particular clock frequency, right? Which is actually given through a oscillator, internal oscillator. And then you have PLL, which is dividing your oscillator clock frequency and providing it to the other module. Now, EPWM module, of course, if that module is working and so many submodules are there, it also needs to have its own clock. Clock is like a key to any particular device. So once you put on your key to any particular device, it will, and you lose the key, it will start working. Okay. So it is like that. So EPWM clock is there for your EPWM module, but time-based clock is there for your time-based module, time-based sub-module. So time-based sub-module has its 16-bit counter, which has its own clock, that is time-based clock. And this time-based clock is a pre-scaled version of your EPWM clock. Now, what is a pre-scaled version? Pre-scaled version in the sense a clock divider is present. Why clock divider is needed? Because suppose EPWM is operating on 100 megahertz, one EPWM module, then all the time-based module that is counter in here that cannot operate at the same frequency because you have to synchronize all the operation of all the modules. So in order to do that, this time-based module should work at a lesser clock frequency than your EPWM clock module. And that's why here comes into the picture of clock prescale. Now EPWM clock will not be also of 200 megahertz. Okay, this EPWM clock is also divided by certain clock prescaler, which is actually faded from your main clock, which is of 200 megahertz. So that 200 megahertz will also have a clock prescaler, and that will give you your EPWM clock. So how to explain that? If you go to your technical reference manual, and from here, if you go to EPWM, I'd like to show you one very important note. Yeah. From here, you can see the type of module that we are studying is a type 4 type of EPWM module. Okay. And this type 4 type of EPWM module, it has a clock divider. Okay. And that clock divider is actually your system clock divided by 2. It means if your system clock is of 200 megahertz and you are having an inbuilt clock divider which is of 2 value, then your EPWM clock will be of 100 megahertz. Understood, everybody? So what I am trying to say here is that your EPWM clock will be obtained from your main system clock, and it is having a clock divider of 2. Thus your EPWM clock will be operating on 100 megahertz and your system clock was operating on 200 megahertz. So this is how a clock divider works. So you can see here this type 4 EPWM module, it has an inbuilt divider which is actually divided by 2. So your clock will be operating on 100 megahertz. So this is a very basic point that you need to remember. Okay. So what I want to say is your operation will not be there at 200 megahertz when you are operating your board at 200 megahertz of clock, but your EPWM clock will be at much lesser frequency than that particular main clock. Now, similarly, your time-based clock is there. So this time-based clock as well, it is divided through a clock prescaler. Now the clock prescaler to this time-based clock is divided into two resistors, and that two resistors are main clock and high speed clock, that is clock division and Hsp clock division. Okay, so that I'll explain how that is. Okay, so that two registers, which is main clock and Hsp clock I'm talking about, you can assign different value to this particular clock and you can set your time based clock. Okay, so what is the default value of that particular resistors, that also we'll talk about. So before that, you need to understand that clock, whenever you are going to operate any counter or anything, it will go on reducing. Okay, it is not like your main counter will operate on 200 megahertz and your EPWM is also operating on 200 megahertz. That was the basic purpose to tell all these things over here. After that, this particular counter has a period register. Okay, since this is a time based module, this period register is called as a time based period. Since it is a time based counter, it is called as a time based period. Now why it is called as a time based counter? Because it is based on your main clock. It is based on your main clock timing. So that's why they have named it as a time based counter. Now this time based counter has a period register, which is a time based period register. Now you will say why that time based period is there? Because that time based counter value, which is 0 to 2 to the power 16, that will be stored in your time based period register. Okay, so this time based period register is for users use, that is it is for our use, that it is our wish. If you want to put some value for any counter from 0 to 2 to the power 16, so we can put that value into time based period register, and this time based period register will actually determine the frequency or time period of your PWM signal. Now how that will happen, that I will tell you in a minute. Before that, you need to remember that you also have a shadow register over here. In order to understand the concept of shadow register, I'll tell you an example. Let's say it is not useful to you in any aspect, but you should know okay, why it is there. So it is there. Let's say your time based period register is updating continuously. So if it does not have a backup where it can store its previous value before taking the actual value, then it will be causing little bit mismatch into that value, and you will not have clear understanding. You will not get accurate value of what is the value of that time based period register. Okay, so what exactly happens is you have a shadow register which actually previously stores the value of period register before getting loaded into it, so that it has its own backup. So whatever actual value you are putting with certain delay due to microcontroller peripherals working and all, this shadow register, it's have its own memory, and it is related to your main processor, that can be then transferred into your period register. So the shadow register, you can take an example like if your CPU is there and it is executing all the instruction, and let's say certain other interrupt is being called by you, and if your microcontroller is jumping onto that address, then your previous address your microcontroller needs to remember, right? Key to which address he needs to go back in order to continue its execution before going into that particular interrupt. So what he does is it stores its that particular destination from here he was jumping to interrupt into a register called as program counter generally. So that program counter remembers the location of microprocessor. So whenever the interrupt task is complete, that microprocessor will go to that program counter and it will start executing its instruction one by one once again. So that program counter, it's like a shadow register. So let's say if you have put some value into period register, and then your microcontroller is coming to that period register in order to ask him the value. So let's say period register has that value previously, and now shadow, why shadow is coming into the picture? Because there will be certain delay with respect to your microcontroller main execution of period register instruction and your main instruction. So that shadow will give you that backup delay. So that shadow register will store the value of that period register particularly. Okay, so it's the use of that shadow register. Then this was about time-based submodule. Okay, now how do we decide frequency of this PWM and all, and how do we actually generate the PWMs? Okay, that I will explain now. So till here, does anybody has any doubt? Does anybody has any doubt? Okay. Okay, Som is not there with us, right?
So actually, he has been called for some work.
Okay, fine. So I will send one whiteboard request if it is possible for you. Okay, you can accept it. We'll see whether I can write something into this board or not. It will be little bit easy for me. Okay, it will be little bit hard to write with this, I guess. Okay, anyways. So you understood till this point what I wanted to say. I think it's clear to everybody. So what I want to say is my screen visible to everybody?
Yes.
Okay, so from here, we saw that our EPWM clock, okay, it was at system clock divided by 2. It means our EPWM clock was working on 100 megahertz. Is it clear to everybody? Now,
Yes, sir.
now we have a time-based clock. This time-based clock is actually divided by your EPWM clock through clock prescale, right? This clock prescale, till here we saw, right? So this clock prescale, it is having two resistors, as I told before. One is clock division and another one is Hsp clock division. Okay, so I will reduce its size so that it comes in the one way. I think it's fine now. Okay, so we saw that our EPWM clock, if it is working on 100 megahertz, our time-based clock will be working on EPWM clock divided by clock prescale, that is clock division and Hsp clock division. So that can be equal to our main clock of 100 megahertz. It will be divided by our clock division into Hsp clock division. Now I can set any value over here into this clock division and Hsp clock division in order to have my time-based clock, right? So let's say if I'm setting this value as 1 and this value as 2. So I'm putting here clock division as 1 and Hsp clock division at 2. So what will be my frequency? It will be, I guess, 50 megahertz, right? So 50 megahertz, it means the time for my TV clock, it will be 20 nanoseconds, right? So what time I'm talking about is it clear to everybody? Like we saw in the presentation, this time for time-based clock, the time which I'm talking about is actually this time, T clock. Okay, is it clear to everybody? This is the T clock timing. So I'm saying if my clock is operating, because this is what my time-based submodule is doing, right? My time-based submodule has a time-based counter, which is running from 0 to certain value. And that's why the clock frequency of that time-based counter, okay, and the timing for that counter will be T clock. Am I correct? So I'm saying that time for a particular counter to rise from one step to another step will be 1 divided by the frequency of that particular time-based counter to which I am operating, right? So is it clear to you all? Okay, so the time for time-based clock is 20 nanosecond. Okay, what I'm doing here is I'm going to tell you how do you obtain the formula for generating EPWM pulses frequency. So it is very necessary for you to understand what I'm exactly saying over here. Okay, because we are very near to understand the formula of that EPWM. Okay, now before going into that, okay, so this was till here everything is clear to everybody, I guess. Now, as I talked about, there are two resistors into time-based submodule. One is time-based period resistor, another one is time-based counter resistor. So what my time-based counter resistor is doing, TBCTR, what it is doing is raising its value from 0 to 2 to the power 16 because it is a 16-bit counter. And this is a counter which is performing the operation. Okay, but where I need to put all this value? Into a register called as TBPRD. So TBPRD will have value from 0 to 2 to the power 16. So this is the operation that your counter is performing. Okay, this is the operation that your counter is performing. And it is counting from 0 to 2 to the power 16. Okay, and what is the timing for each step? That is 20 nanoseconds. Got it? The time for each step for counter to rise from 0 to 2 to the power 16 is equal to 20 nanoseconds. Now, in this slide, if you see, there are three types of counter shown over here. One is up count, another one is down count, and third one is up down count mode. So in up count mode, you can see my time-based counter is starting from 0 and it is counting up to TBPRD. So TBPRD is a time-based period register which is having certain value which is limited up to 0 to 2 to the power 16. And time-based counter is a counter into that time-based module which is performing this operation of counting. And what is the time for counting each and every step is TB clock equal to 20 nanoseconds. Okay, now this is about counting. Now you can see here, similarly, your countdown mode, like let's say if you're operating your counter in countdown mode, your TBPRD will start counting from TBPRD to 0, then again it will start, then again it will reset to 0, then again it will start, then again it will reset to 0. So it is a down count mode where you are counting from 7 to 0 as we saw in down counter. Now we have up down counter in which you will be counting from 0 to TBPRD and then from again TBPRD to back to 0. So this will be responsible for creating your symmetrical waveforms. Now you can see LO dots over here. What these LO dots mean is your compare values are particularly touching onto those waveforms onto those particular points. So we have another submodule here which is coming into the picture which is called as a counter compare submodule. So what this counter compare submodule does is it consists of 4 resistors: compare A, compare B, compare C, and compare D resistor. So compare C and compare D resistor are used for event trigger application. Like let's say you want to trigger a certain event, a certain period of time. So you can use this compare C and compare D resistor. Why? What I mean by event is I mean interrupt only. Like we saw in interrupt, if I'm creating any interrupt, I go on performing another task. So let's say I want to create certain event at certain particular instant where let's say I'm rising on this value and I want to create an event where comparator is touching up value. So I can create the event with the help of the comparator C and comparator D. So these are the non-accessible registers to you. Okay, you cannot put any value into these registers, but only compare A and compare B are there which are available to you in order to program so that you can generate the PWM pulses. Now how can you generate the PWM pulses? Suppose this TBPRD value is 2000 and I'm putting 1000 into this comparator A and 1000 into this comparator B. Now what will happen is this comparator A will be there in middle. Similarly, comparator B will be there in middle and your time-based period will be at 2000. Now there are actually 4 events from this picture if you see. One is at 0, another when time-based counter is touching comparator A, another one is when time-based counter is touching comparator B, another one is when your time-based period is having your time-based counter is having value which is equal to TBPRD. So how many events are there into this particular one? 4 events are there. What are the 4 events? First event is your TB counter can be equal to 0. Another event is Another event is if your time-based counter is equal to your compare A value. Third event is if your time-based counter is equal to your comparator B value. And final event is your TB counter is equal to your TB TRD value. Why I'm saying like this? Because this counter is incrementing. If you observe this comparator to be constant, but your counter is counting from 0 to TBPRD, and then again it is getting reset. So you have 4 set of events which you can trigger, to which you can generate the pulses. Like I can generate the pulse at 0, I can ask pulse to get reset at TBPRD, I can ask pulse to rise at comparator A, I can ask pulse to rise at comparator B, whatever is my wish. According to my wish, I can program this particular pulse at what value I want to generate. Now let's say if TBPRD is here and comparator A or comparator B is in between somewhere here, and if I say that I have to trigger my pulse when this comparator A or comparator B is touching the middle way, then my duty will be 50%. So if this comparator A and comparator B will be having half the values of TBPRD, then your duty will be 5%. If it is having 10% of this TBPRD, then your duty will be 10%. So depend on your comparator and action qualifier. Action qualifier is what? Another resistor that I am using to set and reset the pulses. See, every time whenever you are setting certain values into this, you need another sub module which will tell you that when you have to set and reset the value. So in that case, what comes into the picture is action qualifier. Action qualifier is responsible for taking any action for generation of your PWM pulses. So whenever, let's say you have certain events over here and you want to generate the pulses, and I'm saying at comparator A, I want to on the pulse, and when comparator A touches the downside of the pulse, I want to switch off the pulse. So that is in my hand whenever I want to on the pulse and off the pulse at particular period of instant, particular comparator A, touching comparator A event, touching TBPRD event, touching zero event, it depends on me. I can even set it at TBPRD event, and then I can reset it at zero event. So how, in that case, how my pulse will be? It will come from here, it will rise at TBPRD, then it will stay on for that period of time. And if I'm resetting at zero, it will go again zero. Again, same time it will be zero till here. And if I'm setting it at to rise at TBPRD, it will rise over here. Then again it will be constant, and at zero, it will be again zero. Now imagine that this is so flexible that I can try to create my pulse at any period of time. But what will be the exact frequency of my pulse? That will depend on the time duration of this particular counter. Like my counter, if it is rising from 0 to TBPRD and from TBPRD to 0, it means I am tracing this TBPRD value twice, right? So from here, if you see, this pulse which is rising at comparator A, and this pulse which is again rising at comparator A. So you can see from here that this particular pulse, whenever you ask him to rise and fall, okay, there will be no issue. You can ask to rise him over this event, you can ask to fall him over this event, any event. But your duty may vary. Whatever you want to put in comparator, your duty will vary according to that. But your PWM frequency to which your signal is generating, that will be constant, because your TBPRT is constant, and every event is repeating after a certain period of time. So that's why the frequency of this PWM pulse will depend on what TBPRD value you are putting it over here. Let's say, I will explain this. Let's say this is a 3-bit counter. Okay, now what I have is, I have certain time here, T clock. Okay, and this time period is around 5 nanoseconds or 10 nanoseconds. And how much value it is taking in that 5 nanosecond is 2 cube, that is 8. Okay, so what will be the total time period of this? It will be equal to T clock into 8 nanoseconds. Am I correct? You are rising step by step with certain period of time. So what will be your value? Your value will be T clock into 8 nanosecond. If this is 16, it will be T clock into 16 nanosecond. If that is 18, then your value will be t clock into 18 nanosecond. Okay, so in this case, this is what the total time for any particular PWM. So this total gives you time for pulse width modulation. Like let's say you are setting your pulse over here and you are clearing it over here. Then what will happen is you will have a duty, but you will have a frequency which is equal to this total TBPRD. So the frequency of your pulse, okay, the frequency of your pulse it depends on your total time. Okay, and that time, let's say you are giving it as TPWM, it will be equal to 2 into what is the time for each clock to rise into your TBPRD. And how will you obtain the frequency of your PWM? The frequency of PWM will be equal to 1 by TPWM. So, how I am writing this 2? This 2 is there because I'm using up down counter mode. Let's say I'm using only up count mode. In that case, it will be 1 because in up down count mode, that TBPRD will be traced twice with this particular time. So if you have 2 here and TB clock of 20 nanosecond and you are having TBPRD of 2000, then your total time period will be 2 into 20 nanosecond into your 2000. And that total will be divided, 1 divided by that total product will give you your frequency of PWM. Understood? Clear to everybody? Till this point, does anybody has any doubt? Okay, so if anybody did not understand anything, they can ask me. Okay, so this was there, and this is how you write particular frequency of your PWM. Okay, we'll verify this through our code as well. What is the frequency of our PWM? So now you can see from here, from this slide, that your PWM frequency, it depends on time for time-based clock. And your time for time-based clock, it depends on your clock dividers. And these clock dividers are in your hand. Like you can set the value of this clock division and Hsp clock division. And according to that, your time for time-based clock will be there, right? So this is a frequency of TB clock. Then you will have your time as 1 by TB clock. Okay. So this time for TB clock is actually came from 1 by TB clock. So TB clock is nothing but frequency, and this TB clock is a time for time-based clock. Okay, so this is 1 by 50 megahertz, which will be equal to 20 nanosecond. And this time-based counter will be start counting from 0 to 2 to the power 16. So you well understood. There are actually 3-4 registers that you need to remember. One is your TBPRD, then your comparators, and then your action qualifiers. So action qualifiers will give you action when to set and when to reset any particular PWM pulse. That will be clear when we'll see our code. Okay. So basically what is happening is we are generating EPWM A and EPWM B through this 4 particular things. Okay. So you don't need to remember this. This I've told you already. What is the formula for PWM? I've told it in a more simpler way so that you guys will understand. From this, I guess it is clear to you how to set frequency for your main PWM. Is it clear to you?
Yes, sir.
Okay. Is my screen visible to everybody now? Are you saying something? Just hold on for 2 minutes. I have to open another version of CCs. In order to demonstrate you the code, we'll see how it exactly happens so that it will be easy for you to understand. So this was about the theory of EPWM. Okay, there are many things to happen into this one. It's not like it's over. There are many sub-modules that we have to look into and how they are going to help you while designing your algorithm from a particular file, like how PWM chopper is used, how deadband is used, how trip zone is used, that we'll see. This digital compare submodule is there in order to expand the capabilities of your trip zone submodule. Okay, like if you want to generate certain trip zone events when you want to compare two digital signals, then it can generate your interrupt to pi block as well. Okay, so this digital compare is there in order to expand the capabilities of your trip zone. Then you have input crossbar, that signals coming from one particular pin to another particular pin. Then you have EPWM crossbar, that is signals routing from PWMs to PWMs or PWMs to input or input crossbar. So that we'll see how exactly the exercise for that will help you to understand. Since every submodule has its detailed explanation, I'll take everything one by one so that you will not get confused. Then you have a peripheral, then you have event trigger register, which can trigger any event such as SOC event or trip zone event to pi module or ADC module. We'll see ADC and DAC as well, so don't worry about it. And there are certain things that you need to understand. So I'm showing you a little bit of code so that you get familiar with the registers. What frequency pulse it is generating and all, we'll see that on oscilloscope as well. Okay, once it is available, if probably in the afternoon session today, if it is available, we'll see the output of any pulse. Whether we are setting the frequency formula is correct or not to verify that particular thing, we'll see into the oscilloscope. We'll take more exercises, like one exercise we'll take where we'll route the signal from the board into the board itself through ADC, and when we'll change the potentiometer, we'll see that the level of that signal will be changing by adding the resistance into it. So that exercise also we are going to see. One more thing I would like to tell you is, if somebody is looking into, I think someone was interested into variable frequency PWMs. So from here, if you see that if your comparator are varying continuously, your frequency can be variable. Okay, let's say if your comparator is changing continuously from 0 to TBPRD and you have set and clear the EPWM pulses on particular event or particular time or particular values, then what will happen is it will try to follow its instruction. But since comparator is changing continuously, since comparator is changing continuously, what we can say that your pulse frequency will be, your pulse duty will be changing. Frequency will be constant, your pulse duty will be changing. Okay, we'll see how to generate other things as well, like in variable frequency way, how we can do that. So your duty will be changing if you vary this comparator particularly. Okay, and frequencies will be constant. We'll see how to use it for variable frequency as well. So I'll import an example of EPWM. I'm repeating this process so that you'll be get little familiar when I'm doing it here. you can go to software, and then here there will be list of examples. So you can click on EPWM up down counter and EPWM up counter. So from here you can see that some of the registers that I was talking about is the TBPRD register. So this is a EPWM1 module, and this is a predefined keyword which is initialize EPWM1 example. Okay, so there are whatever PWM is given to you, all the examples will be there. So all the predefined functions, like we saw yesterday, that every function has its API associated with it. So just like this, EPWM.C is also an API which is related to EPWM initialization. And from here we can see that all the initialized EPWM1 GPIO, 2 GPIO, 3 GPIO, all the PWMs are initialized through GPIOs. Okay, so this will be initialization of EPWM1 GPIO. Then you can see here that in GPA MUX1, GPA 0 is set as 1. So whenever GPIO 0 in A MUX1 is set as 1, it means the GPIO 0 is now acting as a PWM1A, and GPIO 01 is acting as a PWM1B. Okay, so like this, EPWM pin 2 and 3 are initialized, and in this one, it is selected through GPIO and peripheral muxing. So I hope it is clear to you how any particular pin is set as PWM and as well as GPIO. Okay, so when it was 0, it was acting as a GPIO pin, and if it is 1, it is acting as a EPWM pin. From this EPWM, you can see that there is one register, that is EPWM registers.tbprd. So this tbprd is a time-based period register that we saw, which belongs to time-based submodule, and it is having value from 0 to 2 to the power 16. Right now, user has given it to the variable EPWM1 timer time-based period. He must have defined this value over somewhere in the initial time. You can see here he has defined 2000 value in a period register. Okay, so he has assigned 2000 to EPWM timer time-based period. So that value is there into TBPRD. You can as well give it directly here. Okay, you can, if you want to put 2000, you can as well put it here as well. So there will be no issue with that. This register we'll see later. It's belong to time-based phase shift. How to add a phase shift between PWM module? Okay, it is selected through this TBPHS register. This is your time-based counter. So time-based counter, you have to assign it to 0. Whenever you want any phase shift, your TBPHS value should be equal to your time-based counter, so that your counter will start incrementing from the phase shift which you have put. So your triangle will not start from 0 now, it will start from the TBPHS value. Okay, in that way you will already have a phase shift between two modules. So we'll see how to do that as well when we'll have oscilloscopes. So we have a comparator A over here, comparator B over here. So you can see in this comparator A register of comparator A, he has set some minimum value of comparator, maximum value of comparator B. So you can put anything over here. So comparator A is responsible for generating EPWM1A, EPWM1A, and comparator B is responsible for generating EPWM1B. Okay, so EPWM1B signal will be generated if you are having, sorry, I make a mistake. It's not like this. And we'll see how we can see. Actually, you have flexibility in action qualifier as well. So this was about comparator. You can put any value into comparator A and comparator B, but this value should not be more than your TBPRD. Okay, if your TBPRD is 2000, it should be 2000 within. If it is more than 2000, then what will happen? You will not able to get any pulse because comparison will not be happening. Okay, so it should be from 0 to your TBPRD, whatever value you are setting. Okay, then you have a counter mode here. So TB control register, this is TBCTL, which is a TB control register, and it is used in order to set your counter mode. So one bit into this time-based counter, time-based control register is a counter mode bit. Counter mode bit is there in order to set any particular mode for turning on and off the pulse. So if you set here up down, it means your up down counter mode will be on. If you set here up, your up count will be on. If you set here down, your down count will be on. So you'll have only asymmetrical waveforms if you're using only one counter mode. If you're using both the counter mode, that is up down counter mode, then you will have a symmetrical waveform, that is triangular waveform. And now you must be thinking why this TB count up down is written here, why not others? So you can, what you can do is you can just copy this TBCTL, okay, and you can go to your technical reference manual, and if you put search over here and if you go to TB control, okay, yeah. So from this time based control register, you can see these are all the bits of that particular time based register, in which you can see particularly bit number 0 and 1 belongs to counter mode. So in this bit 1, bit 0 and bit 1, okay, belongs to counter mode. If you put 0 0, it will be up count mode. If you put 1, it will be down count mode. If you put 1 0, it will be up down count mode. So 1 0 in the sense, if you convert this binary into decimal, it will be 2. So if you put 2, it will be running in up down count mode. If you put 1, it will running in down count mode. If you put 0, it will running in up down up count mode. Okay, so you can see from here that this TB count up down has already a macro expansion of 0 cross 2. So it means the value of this is 2. So it is running in up down count mode. So these are the predefined variables which are there into your, I guess, somewhere in EPWM defines.h header file. So in this header file, you can see all the examples which actually taken all the predefined variables are shown over here. So if it is a count up, it will be having 0 value. If it is count down, it will be having 1 value. If it is up down count, it will be having 2 value. Okay, so it is like that. Now similarly, you can see this is another bit of time based control, which is phase shift enable. So we don't want phase shift right now, so we have put it here as a disable. You can as well put it here as an enable, but you have to see first what enable is assigned to. Okay, so from EPWM defines.h, you have to see TB enable is set to 0 cross 1. So even if you put 1 here in this particular thing, even if you put 1 over here, okay, it will be enable. And if you put 2 over here, sorry, if you put 0 over here, it will be disable. Okay, so this is to disable phase shift. So if you want to enable phase shift, you can put some value over here, like let's say you want to have phase shift. I'll tell you that later. So another thing I want to tell you is time based control register 2 bits, that is clock division and Hsp clock division. So what bit of twist over here is, as I told you, there are two clock dividers, two time based control, that is EPWM clock, and we saw from presentation that your time based clock, it is divided by clock division and Hsp clock division. Sorry, your EPWM clock is divided by clock division and Hsp clock division. And I have multiplied here by 1 cross 2. Okay, why I did that is because if you go to yeah, so is it visible to everybody? From here you can see, okay, from here you can see these are the two bits, clock division and Hsp clock division, of which register? Time based control register. Okay, it belongs to TBCTL. TBCTL bit we are choosing, so that's why we have written here TBCTL dot bit. Okay, So dot Hsp clock division bit we are choosing from here. So if we are looking into Hsp clock division, we can see by default on reset, this clock division is set to 1. Okay, so even if you put 000, okay, it means it is by default on reset to 1. So whatever value you put in clock division, if you put 000, it will be divided by 1. If you put 1, it will be divided by 2. If you put 2, it will be divided by 4. If you put 3, it will be divided by 8. Why 3? Because 8, 4, 2, 1. If you convert it into decimal, it will be 3. So if you divide it by 3, it will be divided by 8. After that, the more you go on increasing this clock, the lesser clock frequency you will be having with your time-based clock. You don't want that, of course, it is a disadvantage. But if somebody wants to work at a lower frequency, it's for them. Okay. Now you have Hsp clock division. So Hsp clock division, it is by default on reset, it is set to 2. So even if you put 000, it will take value as clock divider by 2. Okay. So your time-based clock will always operate on 1.2. Okay, so if you put 000 into Hsp clock division, it will not be divided by 1, it will be divided by 2. And when you are putting 1, it will not be divided by 2, but it will divided by 4. Okay, so there is a mistake in this technical reference manual over here. So when you run your program, you will understand what I was saying. So by default on reset, this clock is put to 0, and by default on reset, if your clock will be go to 2. So your time-based clock now, which is a formula given by EPWM clock divided by Hsp clock division, and main clock division will be 1 cross 2. Okay, so if it is set at time-based division 1 and 1, it means their value is 0. Macro expansion is 0. From here you can see its macro expansion is 0. So this is defined as 0, it means it will be 1 cross 2. Okay. So then you have a shadow mode resistor. You don't have to change anything over here. What you have to put is as it is this resistors. What does it mean is you are loading your comparator resistor when your compare counter starts from 0. You can as well load your comparator resistor when your compare counter starts from TBPRD. So there are two events that you can start from. One is from 0 and another one is from TBPRD. So it will help you to maintain the synchronization as well. Okay, so you don't have to do anything. Whenever you are triggering all the modules, you have to comparator, you have to load onto 0 or time-based period all the time. Okay, then you have a shadow mode. You just have to click here CC shadow. Okay, you don't have to worry about these instructions much. Then you have an action qualifier. So in this action qualifier, you can see that action qualifier CTL-A, what does it mean is action qualifier control A. So in this bit, you are selecting comparator A, up count. So what does it mean? Whenever your comparator A touches the up slant of your counter, it will set the pulse. Okay, and when it touches the down slant of your particular counter, it will clear the pulse. So in this way, control A is used for generation of EPWM A, and control B is used for generation of EPWM B. So you can as well generate EPWM A with the help of comparator B. Okay, like you can set it at comparator B up, comparator B down, and this one at comparator A up, comparator B down, whatever is your wish. Okay, so you can just put set and clear, as this set and clear is already defined as 2 and clear is defined as 1. So obviously if you go to AQCTL-A resistor in this particular technical reference manual, if you go and search, you can see from here that if you're selecting comparator A down bit, and if you're putting 0, it means it is doing nothing. If you are putting 1, it means it is setting EPWM A as low. Then if you are setting 1 0, it means it is forcing EPWM 1 to be high. So in this way, action qualifier will work. So if you put 1 here, your EPWM will be high, that is it will rise. If you put 1 over here, sorry, 2 over here, it will rise. If you put 1 over here, it will clear the pulse. So in this way, you can generate your pulse with action qualifier resistor. So this will be control A will be limited to EPWM 1A and control B will be limited to EPWM 1B. Then this interrupt, we'll talk about this later as we are as time has passed. So we'll look into other things later. So till here, everything is clear to you. Is there any doubt? So I guess now it is clear to you how are you generating PWM frequency. So if your TB PRD is 2000 and your TB clock is 20 nanosecond and your time is you are using up down count mode. So 2 into 20 nanosecond, that is 40, into 2, that will be 16. So 1 by 16, I guess, whatever that comes out to be, that will be your frequency of